Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about James Webb Space Telescope Update 2309-2022. So let's dive right into it. Now, first thing first is Jupiter, the big guy. Now, you have to understand this aspect. Even though this picture looks like it has color, you have to understand the sensor in James Webb Space Telescope is actually monochromatic. Actually, realistically speaking, all camera sensors are monochromatic. They just have a filter on top of it. Or if it's a serious camera, it will have a filter wheel. James Webb JWST also has a filter wheel. So that filter is F306M that is utilized here. So basically take that data. Basically this filter is on, take the sensor data, color it with red, take another filter wheel F212N, color that data with yellow green code, and then take another filter that is F150W2, color it with cyan. That's why you have this false color image. Now why do we make false color? Again, you have to understand at the end of the day, data has to be processed by human. AI does not gonna go to and study this. That's not gonna make any sense. We have to study. We have to understand. We have to evolve our understanding. So we colorize this sort of thing. It also helps us understanding large patterns. So because again, if you just look at the raw data first, you can't look at raw data because our eyes cannot process infrared. So we need to shift that data. We just take that data, shift it. So it's not magic. It's not CGI. It's just shifted data, and that's why I specified this data bin. That's why this color looks so off. It's not just like they are not even trying to. They're just like, dude, this is a scientific image, and again, infrared behaves a bit differently compared to our optical spectrum, so it does have a bit of a different tone. Now, Webb was used, basically NearCam was used for this composite image. Now, interesting aspect of this, even though this looks like just another image, it's much deeper. What does that mean? That simply means Jupiter is very gaseous. What does that mean? That simply means the outer shell is not a shell. There is no quote-unquote crust. So you can look deep into it, specifically in infrared spectrum, because again, that spectrum goes deep. So even though this looks like, if you directly compare it to a, let's say, optical observation, you will find this is like actually much deeper. So what does that mean? That simply means if you take data from both sensors, optical system and infrared observation, if you study them properly, then you can literally create a crust map of this sort of, and that depth of that crust could be hundreds of kilometers. So you can understand how air currents are working. Basically, the sole reason why we have so many weather satellites is one is never good enough. You need multiple data points. This is another multiple data point. Now we can understand how Jupiter's thermal signature works properly, like why this part is hot, why this part is cold, like why this cool is sinking. Again, studying all that data now allows us to understand this far more appropriately. And you can even see the auroras have much bigger footprint than we originally thought. Again, it did not show up that well in optical system. So like, yeah, aurora is there. No, now it's like, no, it's huge. Even though, again, you have to understand distance is also an aspect of it. So we may be looking from a different far. It's like, I think it's no, sir. No, sir. It's a big thing. It's a big thing. It's both direction. It has a big impact. So this is one. And again, its dust ring is also much more visible. So it's one of those things that allows us to deep into the data. Deep into it. Again, for you and I, it's just a weird color image. For anyone scientific, they're like, dude, I can feed this data into gaseous model engines, and now we can get some truly good prediction variable out there. And science is all about prediction. Once you can predict things with good enough reliability, now you know stuff. So that's the Jupiter. Then we come to another boy, that is Neptune. Now, Neptune is very interesting for us simply because after 30 years, we have good images, because you have to understand Voyager 2 was the closest thing that we ever sent to it. And after that, we tried Hubble, but you can see that like it actually went down in terms of resolution, it went down. But we can't blame Hubble. Again, it's a tiny boy, and not to mention ludicrously far away from it. So we can't blame it. But Webb is like, I got this. Big lens. Now you may be like, hey, wait a minute, doesn't that image looks a bit blurry? You have to understand, not all sensors basically or tools they have has different resolution. Some tools are designed for wide fields, they have much higher resolution. Some tools are designed for very sensitive measurements, so inherently they end up with low megapixels. So don't just focus on the, oh, it looks blotchy, it looks very low resolution. It is low resolution. Here's the deal, but its resolving power is far higher. That's why you can see dust rings, which even Voyager 2 images do not have like very crisp image of that. Like again, you can Google proper Voyager 2 image and you can make it out like it's there, but like this is like, look at me, I'm here. So that's amazing, and that's the whole point. You can see optical spectrum, like how the cloud signature is there and how the cloud signatures are moving in thermal spectrum. That allows you to create another weather map. That's interesting and desirable. And this bright boy is Triton. Now, interesting aspect of this, Triton is bright, and out of the 14 known moon, it's one of the brightest. Now, here's the deal. Why the heck it's so bright compared to this puppy? Well, it has frozen nitrogen as shell. What is the shell of it? The shell is frozen nitrogen. That puppy reflects 70% of the light. Now, what is reflecting? It's sun. So inherently, from its vantage point of view, it's getting reflected light from something like few light hours, and this telescope was designed for observing things that are like millions of light year away. So inherently it's getting oversaturated. That's why you see this diffraction spike, and that's the easiest way. If ever you look at unprocessed JWST image and nobody is saying what you are looking at, anything that has this spike either is super bright or super close. So that's why you will never see this sort of spikes coming out of galaxies. Again, they are inherently very far away, so they do not have enough intensity to cause this. But anything that is close by or any star that is very bright will cause this. So that's why Triton is so bright with its own personal diffraction spike. But you can understand, like from a study point of view, this allows us to understand far deeper. Like you can see, there are so many moons. It's like, why the heck Earth is the only one that has one moon? Like I feel so cheated. Then we come to the Mars, the god of war. So Mars was used with all the equipments, that is NIR cam and NIRS spec system on 5 September 2022. Now you have to understand that anytime you are hearing people say that it can allow us to image and study exoplanet, does not mean we're gonna take photos. Let that be very clear. The nearest planet is so far away that the telescope mirror has to be hundreds of kilometers, and then you might get a blob. So what we're gonna get? We're gonna get this. So what does this mean? Basically, you're gonna look at the star. Star's gonna give you an output like this. Now you're gonna observe the light that is coming out of planet bodies. This is very easy to understand, simply because Mars planet does not do too much UV because the atmosphere is very thin. But if you have thick atmosphere like Venus, it will have much bigger impact. If you are talking about Earth, it will have medium effect. So you will take sun signature, basically how sun output should be. It should look like this. Okay. Awesome. Now compare that what it's looking like after it has left the Martian surface. They're like, okay, there are some dips, there are some dips, there are some dips. Basically, there is a signature, exact signature on this basically microns of wavelength that is indicative of some elements, compounds, gases, like carbon dioxide. So carbon dioxide has its footprint, and you can see that water vapor has its footprint. So whenever we can detect water in exoplanet, they can simply means basically you're going to see a graph like this, and which may have a much deeper spike on this 2.5 micron sort of absorption spectrum. That's what people are talking about when they say like we can study exoplanet, you're going to get this data out of it. Another, using thermal system, we are studying the atmospheric behavior of this puppy. Now again, it's a low resolution one, but here's you are observing something that is very faint. It does not mean this is 100 degrees Celsius and the top one is like let's say 0 degrees. It's not very bright. The temperature range that we are dealing with from that far away, it's minute, but it's a miracle that we can actually observe it. And the fact is that utilizing this sort of IR system, we can study local topology effect, meaning there is a dent there in that basin. That basin is trapping air, and that air is behaving differently compared to the local region, and that's why local regions are a bit different temperature compared to that one. We can study that from L1 Lagrange point, basically. Like, that's amazing. That's the interesting aspect of it. We have things that are going there and studying the whole system, but we can do this from this far away. That's amazing. Imagine a lot of data like this, like collected over the course of year, like let's say 5 years. We're gonna know far more about Mars basically behavior, Mars thermal properties than we ever knew. So that's why another amazing result. Then we come to oops, that is technical issue that happened. And now that happened on 24 August. Mid-infrared instrument, basically MIRI instrument, has modes. Basically how you have your DSLR has mode like shutter priority, aperture priority. Here, think of it this way, it just have boatload of filter wheels. It has one filter wheel, then there is another filter wheel, and then another grating. There are a lot of those. So it has many modes. One of those modes is medium resolution spectroscopy, MRS. Now that mode requires this wheel to work properly. Now this will throw up an error. Now computer has, I think it detected too much current to draw, so it was like, okay, halt the function, sent a red alert to NASA. Now be mindful, it was such a minor issue from a JWST point of view that it's like it's not went to safe mode. Safe mode simply means, okay, I'm broken, please fix me, only then I will turn myself. That's a safe mode system. This was not a safe mode issue. This is like, I think this is not working, I'm gonna send flag there. Now what the moment the flag was there, this basically requirement was stopped. Basically stop trying to spin this puppy. Let us diagnose it, and during that time they will use all other instruments, because every other instrument is working properly, so no need to just spin this puppy up. So they will try to figure it out, diagnose it brick by brick, thorough by thorough, bolt by bolt, and this puppy is here. That is a human for scale, so that puppy is the one that is throwing temper tantrum. So NASA is going to look into it, and they have a committee, and again it will take time to study, because again you do not have this, it's in the vacuum of space. What has happened? Again, you can do all the testing in the world, but what exactly broke this puppy, we do not know. And again, it may be just a glitch, it may be a fault, may have happened. This sort of thing does happen. Heck, we are dealing with this sort of similar thing in SLS. So something bad happening to something that is actually in deep space, not that big of a deal. So why this went down, nobody knows. While I'm making this video, maybe by the time this video comes out, you may have seen it. But so far, NASA is trying to fix this from the ground, and again, there is no other option. And hopefully, this is just one-off issue. If there's an issue, it should be a one-off issue. But again, if it shows like there may be some issue, let's say there is some issue with power delivery system, which may be sending too much current to the motor coils and frying motor coils, and that's why like motor coils are not working as expected. That's a very serious issue, because be mindful, there are way too many moving parts in JWST. Like not just the mirror and all that. There are a lot of filter wheels, and all of those wheels needs to work perfectly, otherwise the end of the mission. So this is just one instrument. There are many more like this, many spinning parts. So hopefully this is just a one-off or something glitch, something minor, because if this is big and if this is something that they can predict that, oh, it might wreck other parts also, now we are in trouble. Then again, they will have to do very quick software patches, and then they manually might put JWST into safe mode. So that's the technical issue. Hopefully nothing bad will happen. Worst case scenario, this goes down. That's it. And but again, JWST will work without that much of an issue. It's like, yeah, I'm good. I'm like, I got this. I'm good. Then we come to the fake news part. Now, I deliberately delayed this puppy as far as possible. The reason for that is the title that was going around. That was so stupendously stupid that I literally thought nobody's gonna give gas to this puppy, but I was proven wrong. JWST disprove Big Bang. Whoa. I have no idea how the heck people fall for it. I have no idea. Now, I do understand some aspect of it, because again, if you do not know about cosmology, you inherently don't understand Big Bang. And it's not a fault of yours. Like, again, you may be married, you may have a job, you do not have spare brain power. Again, that's understandable. That's life. You let's say you are a doctor, you know medical things. You are an engineer, you know engineering things. Cosmologists, they know that stuff. So there's a very serious void in our knowledge. But we have to understand one core aspect that I really want to amplify in this video, is that verified science can never be wrong. Let that be sink in. Verified science. What does verified science mean? Meaning which we have empirically tested, predicted, and it has came into, like, you know, we predicted this will happen, and again the tolerance is very tight. Let's say, for example, if you are predicting something that will happen, let's say 100 days from now, again you will get tolerance of, let's say, 2-3 days plus and minus. That's acceptable. But if somebody says this is going to happen 100 days from now and it happened on 50 day, no, that's just lol. That you're just guessing randomly and it came 50% close to it. It has to be very tight. Now, if you do that once, that's not good enough. You have to do it again and again, and multiple people have to do it. That's what makes something verified science. Many people have to do it over the years, over the basically centuries. Even we collect data, and once we have gone through all that hard work, at that point in time, that science, that fact, that theory, that hypothesis will not be proven wrong. All you're gonna do is add more love to it. Basically, you will improve it. For example, humanity has been here for like surprisingly long amount of time. We had written history for surprisingly long amount of time, around 5,000 years. But here's the science is rather recent. Let's say you are very optimistic 500 years ago. Now, how the heck we made so much progress in last 100 years compared to 5,000 years? Because we utilize science as a core metric rather than ideologies. Now, benefit of that is science is building infrastructure. Meaning you build level 1, you build level 2, you build level 3, build level 4, level 5, level 6, level 7, level 8. You keep building on top of it. For example, Newton. Now, Newton comes up with this guy. It's like, hey, I think we have a mathematical model here. People use that model. It works. It predicts things within reasonable accuracy, and even long outers, like, okay, this comet will come up here in this month, in this week, and it's like damn good. Like in some scenarios, the predictions are so good. It's like at 8 p.m. that will happen. It happened at 8 p.m. And again, be mindful, clocks at that time was not very atomically precise, but good enough. So what does that mean? That simply means the science is true. People test it. But here's the Einstein comes along. Einstein is like, I have better. Does that make this guy wrong? No. All it does is, like, this guy had 2 megapixel photo, this guy added 20 megapixel photo. For example, in Hubble photo, you saw a dot that was a planet. When JWST, you saw a planet which had the rings also. Did not disprove the dot. It's just like, hey, more details. That's the critical aspect of science. So if Hubble does something, it will only add to it. It will never subtract from that thing. Again, something temporal can happen. Like for example, the star was there, it went boom, this captured it, this did not capture it, because again, this was launched 10 years after it. That's a different thing. But you will never have that where it's like, oh, I saw this, I theorized this, and this will like, no, you're wrong. No. All it will do is improve it. It's like, I think, dude, your prediction was good, let me make it better. Basically, you build 2-story building, let me build a 200-story building. That's the whole point of it. Science always improves. That's why we started with nothing. We were barely having a telegram conversation, and I mean not modern telegram, like to Morse code communication to like a video call. How the heck that happened? Keep building on top of it. So you have to understand, all we do is achieve a deeper level of knowledge. We never ever like, oh, what we thought was wrong. Again, sometimes there are things that are stuck in that void where like we need a model but we do not have accurate, precise model, so we do our best. That's a different kind of stuff. But something that is verified science, yeah, no, don't ever worry. Like for example, when you are in class 10 in India, you generally study things like AC travels far, AC current, electricity. That is true, but limited. For example, when you go to class 12, you study DC actually goes far. Like if you have to transmit power for long distance, you have to use DC. That's why we use HVDC, because it like saves a lot of power. So for example, China had to transmit around 12 gigawatt from 3 Gorgeous Dam to almost Shanghai kind of area. That took very long of distance, like I think around 3,000 kilometers. If they tried sending that distance with AC, it will not work. Why? Capacitance loss. Again, capacitance loss does not disprove AC does not work. It's just like, hey, AC has some limitations. Like use it within reason. Like use it within 500 kilometers, GG. The moment you try to extend beyond that, you might well look into using DC. Like there are other links in India also that are like connecting 3 regions that are like 1700 kilometers long. Again, that will never happen on AC system because it will lose so much that you will be burning money at that point in time. So they have to use DC. Again, does not disprove Nikola Tesla and like make Edison win. It's just like two different tools, more knowledge. Like for example, Newton, normal classic physics. This system at higher speed, higher velocity, higher gravitational system, this mathematics makes more sense. But if you are doing normal thing, launching normal satellites, just go with this. Done. Go home. Sweet dreams. So this is one thing that frustrated me that much about this. It's like, how the heck people fall for it? Like we have proven Big Bang. Like again, all happened. What actually happened in real time was basically the scientist who was misquoted like hell. It was like, dude, the prediction model that we had, like how tight our galaxy cluster should be, how early the early galaxies could have been formed, that's far more sloppy. We thought like that will happen in let's say 10 million years. It's now happening in like 8 million years. Like how the heck that happened? Again, it did not disprove it. It's just like, dude, you are sloppy, let's make it more precise. And that's why we launched this. That's the whole point of this. And again, in future, we will launch something even grander, even more awesome. And it's going to do even more awesome things. And we're like, whoa, even more tight. That's the whole point. Like 2 megapixel, 20 megapixel. What will future hold? 200 megapixel. That's why like this really frustrated me to no end, this sort of fake news thing. And people fell for it. So this was my presentation on basically James Webb Space Telescope updates. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.